I'm going to work out the second problem down here at the bottom of the page. For each fiber optic cable shown below, you're given the incident light ray and the indices of refraction for each layer. Make the necessary calculations to determine the path taken by the light ray when it hits the boundary. Continue determining the path of the light ray until it either escapes from the fiber optic cable or you reach the end of the cable. Using a protractor, accurately draw in the path of the light ray. Looking at this one, this is the one I'm going to do, I notice that I have n equals 1.8 for this center core, and then above it we have a material with an index of refraction of 1.2, which is smaller than the core, and down here we have an index of refraction of 1.0, which is also smaller. So when the light hits this boundary, it's going from high to low in, so it could have total internal reflection if this angle is bigger than the critical angle. So let's see what happens. First we need to find out the incident angle, and in order to do that accurately I need to extend this light ray. Okay, so about 69 degrees. So let's calculate the critical angle for this boundary to find out whether this is larger than the critical angle or not. So n incident the incident material is 1.8. The incident angle is our critical angle, that's what we're looking for. The refracting material, possibly out here, the second material, is 1.2. And since we're looking for the critical angle, we're going to put in 90 degrees for the angle of refraction. And calculating that, 1.2 times 1, because of the sine of 90 is 1, divided by 1.8, inverse sine, is 41.8 degrees. So, is 69 degrees larger than 41.8 degrees? Yes, it is. So this light ray is going to show total internal reflection. And the angle of reflection is equal to the angle of incidence. So, 69 degrees. Now this light ray is going to go as far as the second boundary. Now the question is, what is going to happen at this second boundary? Well, this is a different pair of materials now, so there's going to be a different critical angle for this boundary. Now, could there be total internal reflection for this boundary? Well, there could be total internal reflection anytime you're going from a higher n to a lower n. So sure enough, this is higher and this is lower. So let's calculate the critical angle for this boundary. So the incident material is 1.8. I'm looking for the critical angle. And the refracted material 1.0, so that must be air or a vacuum. And the angle of refraction is 90 degrees if you're looking for the critical angle. And so sine of the critical angle is 1 over 1.8. So 1 divided by 1.8 inverse sine is 33.7 degrees. So let's find out what this incident angle is. Actually, using geometry, we can predict what it is. So if this angle is 69, this one is also 69, which is greater than this. So it is going to reflect. So we're going to have total internal reflection again. And this this light ray is going to travel in this direction until it gets to this boundary. And that angle is 69 degrees. The critical angle for that boundary was 41.8 degrees. So it is going to have total internal reflection again. I'm going a little bit off my page here. And at that point you're done because you have left the page.